How about teleportation? Now, you know, Bradbury and Company were, you know, they weren't exactly scientists, but they didn't have their head in their sand either. They had been reading some science fiction and some fiction. They sort of kind of knew a little bit about what was going on. Inching our reality ever closer to Star Trek, scientists at the University of Maryland Joint Quantum Institute successfully teleported data, okay, from one atom to another in a container and a meter away. A landmark in the brain-bending field known as quantum information processing. The experiment doesn't quite have the cool factor of body transportation. One atom merely transforms the other, so it acts just like the original. Still, atom-to-atom teleportation has major implications for creating super secure, ultra-fast computers or doing computations in multiple places. When you start manipulating the subatomic particles of atoms, you get some pretty spectacular results, and you're not absolutely altogether sure what they're going to be. Okay? But being able to change that atom over there into something by manipulating this atom is pretty spectacular. Controlling multiple qubits with hyperentanglement. Scientists are quickly putting the single qubit system out of fashion with new setups that can simultaneously manipulate and read multiple qubits. An international collaboration recently completed an experiment involving the control of up to 10 qubits at once using hyperentanglement in simple cat states. While the system doesn't always read out perfectly, the approach could be further refined to produce better results. Because qubit behavior is based in probability, it's difficult to exert a lot of control over a qubit. This problem gets a little more significant as each additional qubit is added to the system, which has limited the number we can entangle at once. To hold down uncertainty and increase control as they add more qubits, scientists are now experimenting with hyperentanglement, or entangling qubits on multiple levels at once. To put that another way, instead of entangling 10 different quantum objects, the authors entangled 2 separate properties of 5 items. In this new experiment, scientists hyperentangled sets of 6, 8, and 10 qubits in cat states for an equal superimposition of 2 states, named after Schrodinger's cat, who occupied a superimposition of the states dead or alive. It's another thought experiment about quantum mechanics. The photons were entangled in 2 degrees of freedom, their polarization and their spatial modes. To get output from the photons once they were entangled, scientists used a special kind of interferometer that could gather information about one of the degrees of freedom without disturbing the other. When the photons were measured, the photons produced the desired state about 60% of the time, with anything greater than 50% considered to be good enough to indicate that the system works at all. The 8-qubit system gives the best results at 7, and there's something about multiples of 8, because the 16-bit experiments with other kinds of entanglement or other kinds of superimposition seems to work pretty well as well. To give the best results of 77.6. Now, if we were shipping you from here to over there, and we only got 77.6% right, we're hoping we get it's the right parts. Okay, so we're a ways away, but the 8-qubit system gave the best results. The greatest limit of the system, according to the authors, was the photon detection efficiency. It's hard to read this stuff, which will need to be significantly improved before implementation can be practical. And so, quit going back to him. We're not interested in him. So, from this perspective, okay, digital visualization works as a tool for seeing things in an entirely different way than we'd seen them before. Okay. This digital stuff produces new attention structures. We get drawn to the idea of things like dynamic stability. Things aren't quite as stable as we thought. They're really quite dynamic, and yet they still seem to function pretty well. The internet isn't quite as singular as folks intended it to be when they set it up, but it still works even though it's pretty decentralized. To the boundary conditions that make lines between objects. You know, it's a very simple kind of experiment in Photoshop. You go in there and you feather a selection. You make a change and you feather it. And what exactly does that do? I mean, if you go into the pixel level and you look at those little boxes, you know, darned if some of them aren't set in one way and some of them are set in the other way, but you can't really make out exactly how they're set. And there are mathematical ways to go in and figure out exactly how each one of those is set. But gee, you can make that soft or hard, you can make it wide, you can make it narrow, and all you're doing is resetting the settings for a pixel. And a pixel isn't anywhere near as small as a subatomic particle. And yet you can produce sharp or fuzzy, gray or black, white, or color in between. And so part of what's happening is that we're kind of getting a sense of instability. We talked all semester long of various different ways that new media has fragmented our environment. Fragmented the media systems that seem to control it, fragmented the business models that seem to be pretty well fixed and work pretty well. In some ways, it's really not strange that new media kind of came to the fore in this sort of post-Eisensteinian era, in this quantum mechanical era. Because, you know, we're getting tools that help us understand these fragments, these oscillations, these different ways of looking at the ways that the world is, the way that things are. And it is a different view than mass media offers. Mass media offers that wide collectivity-like view. It's a picture that tells 1,000 stories. Right? New media sort of goes down to the pixel level and says, well, wait a minute, there really wasn't 1,000 stories. This can be turned a number of different ways. Right? And it isn't one picture, it's actually a number of pictures put together. And they actually have different boundaries, and we're not quite sure where they are. Just as a footnote, you can go follow this one if you want to when you're reading it, because we're not sure that quantum theory quantum theory doesn't explain itself. It sort of explains how Newton doesn't work, but it doesn't explain the universe quite yet. And there are some people who think that maybe string theory does, although there's some indications that it probably doesn't, but yet it seems a little further along in some ways. So if you're interested, you could go look at string theory. It isn't far enough along in providing any answers about how stuff works for me to include it in class, because it's still a little bit too theoretical in terms of its implications. But quantum physics is close enough, because we know with enough experiments that it actually exists. We just don't know what the implications are quite of it yet. You know, we get a different way of looking at things available to us, and you guys are in the middle of it. You will bring to your next exam a machine that is way more powerful than all the machines put together that put a man on the face of on the moon. That laptop sitting right there has more computing power than what they had at the Kennedy Space Center, Cape Canaveral, when those guys were going up and risking their lives in space. I was at Sam's. I don't know what. You probably even buy them cheap. I was at Sam's Sunday. They want $17 for an 8-gig flash drive, and you know, I think you can find them cheaper than that. But 8 gigs for like $17. Any idea how much memory that is? When I came here 24 years ago, we got an Atari. We only got an Atari. Actually, nobody had PCs. The dean had found some Ataris in one of those big box store garage sale things. He bought a bunch of Atari game systems and then refused to give us the game controllers and gave us a little cartridge that ran a word processing program. He said, here's your computer. I think it was a 64K, as I recall. I don't remember, but I mean, those things were infinitesimally small in terms of what they had inside. I think my first AT&T gray box had 32 or 64 megabytes of memory. You know, it changes the way we see things. Right? there is something new about new media. It's not just a replacement for the old. It's built on the old, but it's not just a replacement. There are new things about it. All right, so study hard.